So now I'll go through the concept of battery storage. So the storage market is the next step of the evolution of the PV industry. So for many people who have been working in the industry for 20 years, it has taken a long time to get to this point where it is becoming an accepted technology. However, there is no doubt in my mind that we will see accelerated growth over the next 1 to 3 years as countries around the world, particularly in Europe, will look to meet their emissions target. So traditionally, grid connect inverters, as you know, generate power whenever the sun shines. So this power is then sent to the consumer loads and then into the grids in case there is excess power being generated. However, the generation profile, which you can see here on the yellow curve, does not match the profile of a typical household. Therefore, particularly in the summer months, there will be a lot of power being exported to the grid during midday. And the value of this power being exported to the grid is usually less than the value of the power that is being consumed. So therefore, by adding a battery to the PV plant, you're able to capture and store this energy, which can be used in the morning and in the afternoon. And in the winter months, due to the low levels of insolation, as you can see, there will not be many days when the battery will reach a full state of charge. However, this can be solved by simply adding more PV panels to the inverter, which will then allow you to generate extra power through the winter. So hybrid inverters gives you a good entry into the energy storage space. So what is the logic of the operation of a GoodWe hybrid inverter? So if you can imagine yourself as a PV array, so the PV array is the power that is being produced by the PV panels and being fed into the inverter itself. So if you can imagine that you're the PV array, what happens to your power that you generate? So firstly, the power that you generate as a PV array will be sent to the loads as a priority. And when the PV array does not have enough power to power the loads, then when the PV array has more energy than what is being consumed at the house, then the PV energy will be then delivered into the battery to charge the battery until it's 100% state of charge. So once the battery is a state of charge and there's still excess power being generated by the PV array, then the balance of that energy will then be fed into the grid. So the PV will supply the loads first, then will be used to supply the battery, and then as a third option, it will be sent into the grid if it is allowed. So in terms of looking from the logic, from the load side perspective, so if you can imagine yourself as a household load, such as a washing machine, you will first draw power from the PV array. And if there's not enough power, then you will then draw the power from the battery. And again, if the battery is empty or if there is not enough peak demand capacity from the battery, then you will take the balance of energy from the grid. So that's typically how we use how the GoodWe inverters operate. And this is what we call self-consumption. So we're trying to consume as much of the PV generated power that we've generated over the course of the day. So if we cannot consume it right there and then, what we do is then store it into the batteries and then use the power in the mornings and the evenings when the sun is not shining. So in order to do all this type of work, what we include in our system packages is a smart meter. So the smart meter here is installed at the point of connection. It's measuring the import and export in and out of the customer's home, and it's connected to the inverter via an RS485 cable or an Ethernet cable and sending the information to the inverter, which allows the inverter to calculate how much power it should be sending to the loads, how much power it should be charging the batteries, or how much power should be taken from the batteries and then fed into the loads itself. So we use a smart meter to increase, and the battery storage to increase our self-consumption. So that's basically the main aim of an energy storage system is to use as much of the PV power that we have generated throughout the day. So now I'll take you through the energy storage system topologies. So this is a question that I get asked quite often, because there are a number of, there are two types of topologies or two types of solutions that can be applied. So the first solution that we offer in our portfolio is the DC coupled inverter. So this is showing you a block diagram of how a DC coupled system is put together. So in the middle here, we have the inverter, and on the left-hand side, we have the PV panels and the battery. And on the right-hand side, we have the grid and the load. So basically, the right-hand side is the AC connections, and on the left-hand side is the DC connections. So what we mean by DC coupled is that the PV array and the battery, because they are both a DC power source, they are connected to the same circuit, or they're connected to the same bus. So the PV power that's generated by the panels can directly feed into the battery. So there is no conversion required going from DC to AC and then back from AC to DC to charge the battery. So we are gaining efficiencies in terms of charging the batteries from the PV array directly. So that's what we call, that's simply what we call DC coupled. So when we move to the AC coupled battery inverter, we have the inverter in the middle. And as you can see, on the left-hand side is the DC side, which has only one connection to the battery. And on the right-hand side, we have the connections to the loads and the backup loads as well. So as you can see, on the DC side, there is only one device, which is the battery, which is connected to the inverter. So this is what we mean by AC coupled. AC coupled meaning that the power that is used to charge the battery is coming from the AC side. So that could either come from the grid, or it could come from another grid connect inverter, which is also connected to the loads of the house as well. So when that grid connect inverter is producing excess energy, that energy will then flow back into the battery inverter and charge the battery. So this process results in an efficiency loss between 1 to 3% in terms of the conversion itself. So therefore, you're losing, therefore it's not as if the charging of the battery is not as efficient when you compare it to the DC coupled solution. So as a summary, as you can see, with a DC coupled topology, with oversizing, you have minimal losses in the DC energy because you are directly charging the battery from the PV panels. Whereas in an AC coupled solution, the charging of the batteries comes from the AC side. So, oops, give me a moment. My mouse has stopped working.
Yeah. So Carlos,
yeah.
I take this opportunity to pose a question from the Q&A, because you're talking about, you know, charging from AC towards DC towards the battery. So does this so this also mean that, you know, specifically from the Q&A, 6.5K ET can also charge from AC?
Yes.
So how does this work? Is this a continuous process, or does it depend on the profile you've set? How does it work? Is it something you can set?
No, that's the general work mode. So that's one of the, I mean, in the in the future slides where I'll show you one of the work modes, it's called the general mode. So the smart meter is calculating how much is being consumed, and then it's calculating how much power the PV panels are generating. It's calculating how much power is being charged or discharged to and from the battery. So it makes these calculations, and if there is excess power from the AC side, it will then use that excess power from the AC side. If it comes from the grid or if it's coming from another inverter, it will charge the battery. So the inverter itself is bi-directional. So we can have energy going in from the AC side and going out of the DC side. And then we can also have the traditional way of DC power or energy going into the inverter and then being converted into AC power to the load. So It's basically all done just by calculations. So the smart meter provides information of what's coming in and out, and the inverter is making those calculations of calculating what is the balance of energy and what do I do with that balance of energy. So that's how it's, at a high level how it's done. And it's all done by software. We have software engineers who have programmed this in, I think they use C++. So basically we're just running a closed loop system, which is just taking the values from each component and then calculating and then deciding what to do with that power. So hopefully that answers the question. So in terms of the AC coupled system, when you have an AC coupled system, as you can see from this little picture diagram here, you have your DC panels connected to a grid connect inverter. So if you have a grid connect inverter, which is 5 kilowatts, and you have 10 kilowatts connected to this 5 kilowatt inverter, the AC output that's produced will be limited or clipped to 5 kilowatts. If you connected 10 kilowatts of power to a hybrid DC coupled inverter, you will then, if this inverter was 5 kilowatts, then you would get 5 kilowatts here on the output, and then you may be able to use up to 3 or 4 kilowatts of DC power to charge the batteries. So with a DC coupled system, you're utilizing more of the DC power than you would if you had an AC coupled solution. So this is what we mean by having power clipping by the grid connect inverter. So here, potentially you could have 9 or 10 kilowatts charging the battery, but here in this situation, the amount of power that is used to charge the battery will be limited by the rated output of the grid connected inverter. In terms of system efficiency, the round trip efficiency is generally higher with a DC coupled system, between 3 to 5%. That's generally attributed to the DC coupling, which allows the DC power to directly be sent to the battery itself. Whereas when in an AC coupled system, we are having conversion efficiency losses when we're going from AC to DC. In terms of the backup capacity, which I'll touch on a little bit further into the webinar, in a backup situation, so when the grid is failed, with a DC coupled solution, the backup loads can be supplied by both the PV and the battery. But however, in an AC coupled solution, the backup loads are supplied by only the battery, because in a grid failure situation, the grid connect inverters will shut down, which is the anti-islanding feature, which is designed to keep the line workers who are fixing the problems on the grid safe. So this is another advantage for having a DC coupled solution. So in terms of the applications at a high level, the DC coupled system is a nice solution for new build homes or revamping of old systems. And the AC coupled system is a nice retrofit solution. So if you've only just installed a PV plant over the last couple of years, it probably has the latest PV panels, it probably has the latest inverter. So you don't really want to rip what is essentially a new system out and then replace it with a DC coupled system. So what you can do with these types of systems, then you can just simply add a battery inverter, which is the AC coupled solution, to give the overall system energy storage capability. So this is the retrofit concept. This is typically what we use for the AC coupled solution. So here on the right hand side, we have an old inverter, or it could be a GoodWe inverter, it could be an SMA inverter, it could be a Fronius or Solar Edge, doesn't really matter. If you would like to, or if the customer or the end user would like to add energy storage to his old system, then he can simply install an AC coupled battery inverter to the system as well. However, by extending to or adding an energy storage system, the end user, of course, has the option to install a DC coupled system in addition to what is already being installed. So they could either go for an AC coupled system or a DC coupled system. Both solutions will allow the end user to add batteries to their PV plants. With a DC coupled solution, if they were to add that to an existing system, they would have to add more PV arrays to the roof. So then you effectively have two independent PV arrays working independently of each other.